Hello. Cool. Is it on? Yeah. Okay. Hi everybody. My name is Julian. I'm an Android engineer from Facebook and Instagram. I joined Facebook 3 years ago. Initially, I worked on the main Facebook app and Messenger app in London, and a year ago I moved to Instagram to New York to work on the client performance team. On the client performance team, we work on different areas of performance, like cold start, application size, scrolling performance, and some others too. And in this talk, I will go over some optimizations that we did in recent months and also talk about some performance trade-offs we've seen. But before I go into the details, just let me set the stage for what Instagram at scale today is. So our engineering team has been growing a lot. I think last year we doubled. This year will grow a lot too. Having more engineers means bigger code base, whether it's in the existing features or adding new features like we did recently for Live, Stories, or Shopping. And lastly, at the end of 2017, we reached 800 million monthly active users. And all this growth is amazing. We're very proud of it, but it does pose certain challenges, especially when it comes to performance. We want to maintain this performance long term, but at the same time, we want to remain a lean, small, and fast app. And this is what this talk is about. Yep. Let me start with cold start. Cold start is very important. We all want our apps to start up as fast as possible. Users care about cold start because they don't want to wait. From our experiments on the cold start, we see that cold start wins emerge over time, which means that as we improve cold start and release a new version, we probably won't not see engagement wins immediately. This is a process that can take weeks or months. And the reason is that as users use the app, they notice over time that it gets faster and faster and may engage with it more. Application size is another important metric. We want our apps to be small, and users care about application size because they need to download the application, which means using network, and they need to store it on a device, which will use disk space. Google recently published this data that as you shrink your APK, you will grow installations and also upgrade rates. Or to think about this the other way around, as you add more code, more resources to your application, and it increases your size, it will actually decrease your installations. And they measured it by watching at the metrics of people who go to the Play Store, and based on the size of the application, whether they decide to install it or not. And the data Google published was that if you increase application size by 6 megabytes, this will translate into 1% drop in new installations. And this 1% is also valid for upgrade rates. So less users would upgrade to a newer version with new features, new improvements, and new bug fixes. This 1% is a worldwide average. It will differ by countries, regions. In more emerging markets areas, could be closer to 4 or 5%. In developed countries, it will be 1% or less. Now I want you to imagine that you work on a new optimization in your app. And with this new optimization, you improve cold start, but at the same time, you regress application size. And I will explain what this optimization is in details. But now imagine that if you apply this optimization directly, that's how it looks. You improve one at the cost of another. And this is the nature of the optimization, and you cannot change this. Or you can think another way of this. You improve app size at the cost of cold start. So what would you choose for your app? Do you think apps are different? Some apps need better cold start, some need better app size. So what would you choose for your app? For instance, would you trade 100 milliseconds of improvement to cold start for a 5 megabyte regression in size? What about 500 milliseconds of better cold start for 5 megabyte regression in size? Those are difficult questions to answer. And by we, I mean the family of Facebook apps, Facebook, Messenger, and Instagram. I don't think WhatsApp was involved in this. We faced this dilemma in recent months. that each app had to decide like which way to go. And there is no one solution fits all. Apps are in a different state. Some apps need better cold start and some need better app size. Also those numbers, whether it's 100 milliseconds or 200 milliseconds or 500, those numbers will differ by apps too. We Instagram, we went for better app size. Those numbers for us were, the regression in cold start was between 100 and 200 milliseconds. And then the improvement to app size was around 6 megabytes. And Instagram is pretty good on the cold start and application size. But we thought that the win on the application size is huge. It's like 6 or 7 megabytes. It's a great decrease. Is that we should go this way. Messenger went for better cold start. And Facebook went for better cold start too. For them, the regression in cold start was bigger. It was closer to 300 or 500 milliseconds. But also there's a difference between those two apps and us. Both Messenger and Facebook, they have light versions for devices with limited network and space. Messenger Lite is below 10 megabytes. Both apps are below 10 megabytes. So they kind of have case with the users who need more space covered. Whereas we Instagram, we currently, on Android, we're currently around like 30 megabytes. But like we need to make sure that whatever we have is acceptable both for emerging markets and developed markets. That's why we went for better app size. But then Facebook wasn't fully happy with this solution, and they invested a lot of engineering work. They built optimizations on optimizations to actually get the best of two worlds. But this required a lot of additional work. So what is this optimization specifically that I'm talking here? This trade-off between size and cold start. This is related to the file resources.arsc. If you unpack your application, so our application is just like an APK file, which in fact is a zip file, which you can unzip and look into it. You will have a bunch of files. There will be a classes.dex file, which contains Java code. There will be a lib directory, which contains native code. And there will be this resources.arsc file. And notice how big it can be. So what is this file? This file contains resources like strings, dimensions, drawables, IDs, styles, layouts. Notice that some of the resources on Android have a dedicated file, like a layout file or a drawable file. But some resources, like a string, they don't have a separate file. Like there's one file with all the strings. So this file will contain all the resources that don't have a dedicated file. And for the resources that have a dedicated file, this file will have a pointer to those files. This file is just like an array. It will have resources and a default value for it. And then in your application, you may have many configurations. You may have a landscape mode. You may have different screen densities, different screen sizes. And this file will contain the override values. But if you don't have a override value, this file will contain a null. And this file is not a sparse array. This null value will actually cause bytes. This will take space on the disk. So if you have 1,000 of resources and only 100 of overrides, those remaining 900 nulls will actually take space in your application and on the disk. So what I'm trying to say is that this file not only contains a lot of information, but its structure, its format, for apps with lots of configurations is very non-optimal. So what can you do with this file? You can compress it or not compress it. APK is a zip file, and you decide which files to compress or not to compress. I'm not sure if this is clear. So when you have a zip file with lots of files in it, every file will have an additional metadata file. And this metadata will contain a flag whether this file is compressed or not. It's okay to have a zip file where some files are compressed and some are not. This is totally fine. An Android system when launching your app, will handle both cases, whether this file is compressed or whether this file is not compressed. So if you do compress this file, you will see a few megabyte drop in the app size because you compress it. But then it means then you need to decompress it on every cold start. Not you specifically, Android will handle it. When you click application icon, and before you see your activity, your UI, the system will see that this file is compressed, will decompress it into memory. And decompression needs CPU, which means it needs time. So this will make your cold start longer. Similarly, if you don't compress this file, you will have faster cold start because you don't need to decompress it, but you will have a bigger APK file. Let's continue. If you decompress it, you will have fast access to resources after cold start. The reason is that after cold start, this file is decompressed into memory, and you have fast access to any resource. But this means that if you don't use some of the resources, and you probably don't need all the resources, you will waste memory. If this file is 10 megabyte file, you will need to allocate a 10 megabyte chunk in memory for the whole file. And then if you don't compress it, you will use less memory because operating system will use M-mapping. M-mapping is when you want to read data from a file, and you kind of pretend that all this data is in memory, you reserve a region in memory of the exact size as the file, but you load into memory blocks in a lazy way. Once you want to access a resource, operating system will read in a block with this resource from the disk into memory. So if you don't use all the resources, you will use less memory, which is good. But then it means that you will have slower access to resources. The first time you access a resource, you will have slower access to it because you actually need to read it from memory. So what I'm trying to say is that, this trade-off, whether what to do with the resources ARSC file, whether to compress it or not, is a trade-off between cold start, application size, memory, and resource access time. And there's no one solution fits all. Those numbers on the cold start and application size will look differently for different apps. So at the end of the day, if you want to play with this, you need to measure it and decide what's the best for your app. I think by default, Android leaves this file uncompressed. So it chooses better cold start. Let me now switch to modularization. Modularization is like an Instagram-wide effort that we started a year ago, and the idea is very simple. We wanted to modularize the whole code base. So before modularization, it could look like this. There could be a dense graph of dependencies between features where they shouldn't be. You might have library code mixed up into feature code, or even library code depending on the feature code. So it's a mess. After modularization, it may look like this. You will have features where the code is separated. You remove the dependencies between features. You establish interfaces for the features. And you will extract the library code out of the feature code, and library code wouldn't depend on the feature. And this is good. This is good for many reasons. One, the most obvious, is that you have a more healthy code base. So it's easier to read old code and easier to write new code. You will have better build time because as you work on one feature and modify one feature, you only need to recompile this one feature to build APK. And it also may help with bug triaging, as it's easier to identify the owners of the features, of the code ownership. Another reason is that we are considering approaching Google Instant Apps. Instant Apps is about serving to the users a native experience of a portion of your app without going the standard installation process. And modularization is necessary so that you can serve this one module, this one feature to users. And this is really done to grow engagement, to get more users. Another reason why to do modularization is for better cold start. So on cold start, you usually show this one screen. It could be a one feature, it could be a set of different features. But anyway, you want to execute the bare minimum of code that is necessary to show this one screen and nothing more. When things are mixed up in the code base, you may actually accidentally trigger many other features. So I would say that modularization helps with controlling what code gets executed and when. But let's dip into this case slightly deeper. Classes.dex file is a file which contains Java code. Before modularization, there will be no specific order of classes in this file because it will just simply depend on the build order or your dependency graph. When it's mixed, then you will get this random order of classes in this file. After modularization, it looks more like this. So classes from one feature will be close to each other in this file. The reason this is important is that classes have strong locality. So once you need a class A from certain package, you will most probably need more classes from this package very soon. An operating system knows about this. An operating system is optimized for this case. So when you need class A, the operating system wouldn't read only this one class A into memory. Operating system works in blocks. So it would read a block. It could be 16 kilobytes, but it could be 128 kilobytes. It would read in the whole block from disk into memory. And this block will most probably contain a lot of classes. So if you need class A, but you don't need class B and C, it's a waste. It's a waste of I/O, and it's a waste of memory. But there's more. Operating system has something which is read-ahead mechanism. So when it sees that you need this block, it will assume that you will need subsequent blocks too. So it will start reading those blocks into memory too. So again, if your like order of classes is random, you will pretty much like jump from one place in classes.dex file to another and back to the beginning and back to the end. There is no strategy, no optimization for the operating system to do. So either operating system will just stop doing this, or will keep doing this, and you will again waste resources. So with modularization, you can basically what you gain is that classes that are used together are close to each other. But you can actually take this further. You can apply regex interdex optimization. Regex is an open source project from Facebook, and this is a bytecode optimizer. Like probably we all are familiar with ProGuard. So ProGuard optimizes Java bytecode. Regex is a step further. It works on dexes. The reason it works on dexes is that some optimizations are not possible on the Java bytecode level. For instance, interdex. What interdex does, it will reorder classes in the dex file. So you need a dex file to do this. And let me walk you through how it works. Just to make sure. So regex is a bytecode optimizer with many different optimizations, and interdex is an example of one optimization. And it works like this. Let's say you establish a typical use case for your app. Usually it will be cold starting to your main screen. And then from the running application, you get a heap dump. And then you run a script provided by regex to get a list of loaded classes in the exact order they were loaded. This is step one. Step two. You enable interdex for your app. You include this file with list of classes in your project. And when you build your application, interdex will reorder classes to match this exact order. So in the classes dex file, you will have classes in the order that are exactly in the same order that are needed during cold start. There is nothing better you can do. This is the most optimal order you can have And if your bottleneck for cold start is in I/O, which is like reading things from classes.dex, this will be like the best optimization you can get. Again, at the end, it's all about measuring. Maybe modularization is enough. Maybe this brings more improvements. I encourage you to try it out and see if it improves cold start for you. Coming back to modularization. Modularization also unlocked for us a different project, which was lazy loading. Lazy loading. The concept of lazy loading is this. Initially, you have a classes.dex file with all the features. And you can use your build system, for us it's bug, to actually compile some features out of the classes.dex file into separate files and put them in the assets directory. The reason we did this was that we're hoping that as we get the classes.dex file smaller, it will improve cold start. The assumption here is that the feature A, B, and C are not features needed during cold start. Those might be optimal feature, like optional features or less core features, but features used outside cold start. So if we during cold start need only this classes.dex file, and if it can contain only the bare minimum needed for cold start, this would be very optimal too. Back then, when we started this project, and it was a year ago, we also goaled against method count. I don't know how many of you remember Dalvik runtime, which runs on Android 4 and below. And Dalvik didn't have a native support for going multi-dex. There was also a support from the Google support library. But actually going multi-dex had a certain performance penalty, especially for calls that would go between dexes. So if you have a function in one dex file which would call into a object or a class or a function which is in a different dex file, this call will be expensive. The reason it will be expensive is that some additional verification needs to be done runtime, whether this call is correct. And also code that it runs across dexes is not optimized. So by default, it will be slightly slower. So we thought that if we remain a single dex file, and in the summer 2017 we were a single dex file, then it will help with the cold start for Dalvik users. And back then, and even today, Dalvik users is a maybe not significant, but we have at least a few percent, if not more, of users on Dalvik, which actually for us translates into tens of millions of users. So we definitely want to optimize the case for them. So how we implemented lazy loading? So to load a class, we need to use the standard Java class loader mechanism. This is like a building block, and on top of it, the way that Android works is that Android would have an application class loader which points to the Instagram file, to the APK file, and there will be a system class loader which points to like Android framework, Java, and anything that lives on the device. And those class loaders would create a chain. There would be a parent relation. And so this is without the lazy loading. This is the default case. And the way the class loading works is that if I need class A, the system would go to the application class loader and say, hey, do you have class A? If yes, this is great. This is end. If not, the application class loader would delegate this call to system class loader. If system class loader has this class, great. If system class loader doesn't have it, there's no more parent to ask about it, then a class no definition found exception will be thrown. So we need to, when we want to implement class lazy loading, we need to inject this lazy loading somehow into this picture. One option is to use the Android API, which is Dex Class Loader. Another is we can roughly follow what the support library does for multidexing. This code is open source, so we can check it out. Or we can think of implementing more performant algorithms. Okay, let's try with the Dex Class Loader. So we would create a Dex Class Loader and point it to our feature Dex file. Then we would add this into this chain. But the problem is that if your feature Dex file contains some Android components, like an activity or a service, then this wouldn't work. The reason it wouldn't work is that, notice that we don't actually create activities or services. We just say to the system what activity we want, what service we want, but we don't call a constructor. It's the system that will actually create this object. And the system is not aware of Dex Class Loader. The system would start searching for this class from the application class loader downwards, which means that it wouldn't find it. So this approach works for like a Java libraries, Java features, but not really for Android ones. Another approach is that we can try to follow what Multidex library does. So Multidex library, they modify application class loader by using non-public API. So class loader, it doesn't have an API which says, hey, can you please handle this one more file? No. Class loader once initialized, and it's initialized to our APK file by the system, like there is no public method to say, handle this one more file. But this is Java. There's ways to actually modify private fields in Java. So we can modify private fields in the application class loader so that it would handle other files too. And if you actually look at the Multidex library, you will notice that they have different implementations for different versions because those private fields were changing. If you modify private fields, you will never know when they change. So this approach needs a bit of maintenance, but it works correctly for the activities, services, for any features. Instagram went for a slightly different approach. We injected our class loader in the middle of the chain. And this approach also works for activities, services, etc. And it also modifies private fields. But the field that we modify is the parent field. What's your parent? And luckily, this field has never changed, so we have only just one version. Yep. So whatever approach you choose, at the very end, you will have a list of Dex files, and you will need to load classes from them. The way it's implemented in the support library is you have just a very simple list with those Dex files. And as long as you load classes from classes.dex files, it works fine. It works fine because this file is at the front of the list. But when user navigates to feature A, it means that the mechanism works like this. I want to load a class from feature A, so I will first ask classes.dex file, hey, do you have this class? It will say no. So I will keep traversing the list to feature A Dex, hey, do you have this class? Yes, this is great. But it means that feature A probably has a ton of classes. So for every of those classes, we'll need to repeat this iteration. And now if we want to load classes from feature C, for every single class, whether it's 100 or 1,000 classes, we'll traverse the whole list and query each Dex file whether it has the class or not. So we initially went with this approach, but we actually saw significant performance problems, latency. It was depending on the case and the scenario, but in some cases it was adding a couple 100 milliseconds of latency to load a piece of feature. So we implemented our own class loader. Instead of having a static list, we would have a priority list. So once we load a first class from feature A, we would bump this file to the front of the list. And it would stay there as long as we load classes from this file. When user navigates to feature C, we would bump this file to the front of the list. And with this approach, like a very simple change from a list to a priority list gave us huge performance win. It completely removed those a couple hundred milliseconds latency. Kind of key thing to notice here is that this code needs to be thread safe. You can have like one process, which is your application, and you may have multiple threads. And those threads will use the same class loader. And the class loader has a one common case, which is searching for a class, and more of a edge case, which is changing the order of those files, promotion. And at the same time, you have multiple threads searching or trying to change the order. But it's very, very important that you have no synchronization on the common case, which is searching for a class. If the common case has any synchronization, this will kill the performance. It will be terrible. But of course, as you need to change the order of things on a list and multiple threads run it, you need to have some synchronization, but you need to limit it to the bare minimum. A few months ago, I open sourced the framework for lazy loading. When I was doing this, we still had the simple list implementation. If I have time this spring, I will upload the promotion class loader into this project. But still, if you want to check it out and see how we did this, then feel free to do this. Like today it looks the same. It's just that the class loader is slightly different. Instead of this list, it has a priority list. Thanks a lot. This is all I prepared for today. I'm happy to take questions if we have time. I also wanted to say that if you see me later today or tomorrow, or I think there's a happy hour in a nearby bar today, just feel free to come to me and talk about the performance. Not only if you have questions, but maybe you can tell me what you did for the performance of your app, and maybe I can try to apply it at Instagram too. So yeah, remember my face and like come to me, okay? Thank you. How are we doing with time? 10 minutes.
This is a really cool talk, but I had a question about when you start going through this like class loading, how does that work for other developers like that maybe aren't working on this? Like, is it transparent to them, or do they just say new class, or do they have to they just have to modularize? Is that?
This is completely transparent. Oh. This is even if they need to speak to the class loader class for some reason, then they would still use the class loader, which is a abstract class, and whatever implementation there is, they would never see it. It's all kind of like hidden. They don't need to know. They don't need to know about this. It should work automatically for the whole app, all the threads, the whole process. And it should work correctly. So if a developer wants to load a new activity or a service, it must be doable. It must work.
How do you measure code start?
How we measure? Oh, geez. So it's a complex. So the question is like how do you define cold start? And I feel like every app has its own definition of cold start. You may say when the cold start ends, whether you show the first activity, but do you require that there is the content? And does this content come from the network, or is it cached content from the disk? So like one problem is to define the cold start for your definition. And then there's multiple steps that lead to this, to the end of the cold start. So we measure it separately, and we have like a built-in trace tool to measure it, and then we collect it from. We have some sampled collection from public users, then do some aggregations per per different operating system, different device class for different CPU memory stuff. But this is the data science stuff. I don't know if it answers your question. Cool.
Hey, thank you so much for a great talk.
Thanks.
Anyway, I was in the early part of the talk. You were talking about the compressing versus not compressing different pieces of the APK file, and you talk about the trade-off between download size, right, and therefore download time, and how long it takes to do the cold start because you're uncompressing. But it seems to me there should be a middle ground. I was wondering if you guys, Instagram, had tried it and if you could comment on it, which would be to transmit, right, like an ARSC file or other related assets, compressed, but then store them in userland uncompressed to be then utilized on start. I was wondering whether you tried anything like that, whether something sort of middle ground like that had any results for you, or just any the benefit of your experience.
So, first of all, like to do any of this thing, you need to mess with the Android internals. There is no. The reason is that this thing, whether this decompression or lack of compression, this happens before a single line of your code gets executed. This is done by the Android OS. So you kind of like it's difficult to take control of this process if it happens before your code gets executed. When I said about that Facebook invested more work and built some more optimizations around this, is that they actually decided to download on demand some resources. So in a way, that's like a middle ground, so that they can keep this file uncompressed, but this file is much smaller because the default APK will contain only the bare minimum resources. All the rest will be downloaded on demand. For instance, if you go to the Facebook app and try to switch language from English to any other, you will see that it will start downloading of this the strings of this language because all the other strings are downloaded. So this is like one of the optimization, and they did a bunch of others so that they can keep this file uncompressed, but it's much smaller. Mm-hmm.
Thanks again for the talk. Going back to his idea, I like the idea where you could actually uncompress the application at install time. And if you imagine you have a background service that will be listening for it to automatically launch when your application is installed, then you could imagine uncompressing from that background service before you have even an activity started. So that could actually work, I believe. So you would still compress. Once Android install your application, you would then uncompress it at that time. With a background service that does not require any UI, so that does not require any resource loading.
It could be possible if you, so basically you want to your application, you want to decompress it on a disk, right?
Yes,
and then
install time.
What it means is that you will store it in a different location than it is by default.
No.
Yes, because you will uncompress it to your data directory, because this is where you have access to.
But Android does that for you already.
What's that?
Android does that for you when you install your app. Android is going to uncompress.
Into memory.
No, into disk, into a data partition for you already. And then from there, you have a background service that will go and uncompress your resource file for you before you launch the application.
I mean, and what Android does is Android decompresses this file into memory, nothing more. Android never decompresses this file into disk. If I implement decompression into disk, it means that these resources will have a different location than it is by default. What it means is that I will need to rewrite, re-implement every call site to the resources. So instead of going to the default location, instead of calling get resources, the public Android API, which will go to the default location where these resources wouldn't be, I would need to rewrite every of those cases to go to my custom location and read resources from there. Maybe this is possible.
No, if you uncompress and override the original file, right? If you uncompress it and call it the way Android is expecting it, then you will go and look at your uncompressed file.
But I think the permissions wouldn't let you write the file there because this is...
Your own file? It's your own file, so you have the permissions, you own those files.
I think you have access to data directory, but not to the app directory.
Yeah, but your application data is stored on the data.
So the default data directory is /data/data and then /your directory. This is where you can store things. Whereas where application files are stored and, for instance, where the files are decompressed to, like classes.dex file or native code is decompressed to, is I think data/app. And I don't think that apps have direct access to this directory unless the device is rooted.
So your approach to basically split it into multiple Dex files and then load them. While I agree it solves the cold start thing for you specifically, you would still be paying a penalty on Dalvik machines, right? So let's say it was previously one Dex, now you have multiple Dex files. So on Android 4.0 and above, you will be doing more work rather than less work, correct?
So like in our case, if we didn't do lazy loading, we would go multi-dex anyway.
Yes. If you are already above the 64K limit, yeah, I agree.
Yeah.
But if you have just a single Dex as of today,
Yep.
Splitting up it into multiple Dexes is more on the penalty side rather than the advantage, at least for 4.0 and less, right?
Yeah. So basically, your classes.dex file becomes smaller, which like as long as you have good order of classes, like using interdex or modularization, then splitting this into lazy loading probably has no performance benefit. If you have things which are messed up, and then you do the lazy loading, maybe it will improve the order of classes in the feature decks, but there's other tools to achieve this. Mm-hmm. Cool.
Did you hit into any network latency issues? And if yes, how did you optimize that? Because typical Android REST call can take anywhere from 300, 400 milliseconds to more than a second.
Network latency, in which case?
Maybe the REST call over HTTP. Did you hit into any of those problems? So whenever Android client is talking to backend to fetch data, for example.
Oh, so you don't ask about some specific?
No, just different question.
Oh geez, there's a whole team that works on network performance.
Okay.
It's like almost as big as this room. No, I'm kidding. I think that the topic is too deep. Like they do so many optimizations around like network stuff. So many customizations. Even if you take some like ready open source library, we would still dig into it and customize it for our case. I feel like this is like a long as river, this topic. Okay.
We're all out of time for Julian, so let's give a big round of applause for this wonderful talk that we just had.